Alright, so I need to make a little video to try to help us to catch up a bit here. Sorry I got behind. So this is on the maximum principle. This shouldn't take too long. Mostly there's just a couple little theorems we need to be aware of. And the first one here is the strict maximum principle. Real version. Let u of z be a real valued harmonic function on a domain D such that u is bounded above by m for all z in D. So if u of z naught equals to m for some z naught in D, then u of z is equal to m for all z in D. In other words, if the value of the function reaches its maximum, like the upper bound for it, if it attains it somewhere, then that function's constant. All right, for a harmonic function. So the proof is actually pretty interesting. Not so much because it's something we're going to keep doing, but more because it's an example of a proof which uses topology. So what he does in Gamelin is he defines the set of points S sub n to be the points for which u of z is equal to m, right? And he shows that that set, S sub m, is an open set. But the set of points such that S is less than m, so the set of all points such that u of z is less than m, well, that's also open, it turns out, by the continuity of u of z. So what then you have is you have that the domain is covered by sets for which u of z is equal to m, and sets, points for which u of z is less than m. And these are both open sets. And of course there's no commonality, right? These are disjoint sets, which means then that you've separated D into the union of two open sets which don't intersect. And if you just draw a picture of what that has to look like, right? Right, if you just draw a picture and think about what that looks like, they're open sets, they don't connect. Well, it's impossible for those to be connected, right? You can't connect this point and this point with a path unless you go outside the set, right? So if there's a union of two sets which form the whole set and their intersection is empty, that means that the set is not connected, all right? And so that's an alternate definition of connected in topology, is that a connected set is one for which you can't write it as the union of two disjoint open sets. So that gives you a contradiction then. Well, it doesn't give you a contradiction. So what that means is either that Sm has to be the whole set, either Sm has to equal D, or S less than M has to equal D, right? Because otherwise you'd have a separation of D, which would contradict D being connected, right? But we're assuming D is connected because it's a domain which is an open connected set. So that means either Sm is D or S less than M is D, but this is impossible because we're given that there's at least one point with u of z not equal to m, which means that Sm equals to D, which is to say that u is constant on D. So that's pretty neat. And then once you know the real version, the real maximum principle for harmonic function, then you can get the complex version. All right, so let's see here. It's called the, I think Gamelin calls it the strict maximum principle. Let h of z be a bounded complex valued harmonic function on a domain D if the modulus of h of z is less than or equal to m for all z in D, and there exists a point such that the modulus of h of z naught is equal to m for some z naught in D, then h of z is constant in D. In other words, if the modulus of a complex function is bounded by m, and there's even one point in the domain for which the value of the modulus is equal to m, then that forces h of z to be constant. So if we let h of z naught equals to m e to the I theta, then what that means is that, we can write this if the modulus of h of z naught is equal to m, right? So what I say next here, I say, okay, suppose we have a point z naught for which h of z naught equal to m. It follows that there exists a c in the complex numbers such that the modulus of c is 1. All right. Well, what is that? That c is just the phase here. Well, actually, the c that you want to have c h of z not equal to m is just c equals to e to the minus I theta, right? If the polar form of h of z naught is m e to I theta. So that's what this mysterious c I'm talking about here in this paragraph is. Okay, but then the real part of c times h of z is a real valued harmonic function. Hence, by the previous theorem we just talked about, that means u of z is equal to this constant m. But if you think about that, that means that the real part of h of z is m over c, and it follows that the imaginary part must be equal to 0, because if it wasn't, right, if you had h of z as m over c plus I times some alpha, that would mean that the modulus of z was not bounded by m, because this, if alpha was non-zero, this would be bigger than m. Remember, the modulus of c is 1, so when you calculate the modulus of this, it's at least m when you work it out. Okay, so anyway, but this what does this mean? This means that, well, I mean, the theorem follows. All right, now, oh, I said, but you may recall we showed all real valued holomorphic functions are constant. So, okay, so yeah, this point, so we proved here that the function's real valued, and then we referred to the previous theorem that we proved using Cauchy-Riemann equations and such, and that establishes that this function is in fact constant, h of z is constant. And then we have the maximum principle. Here, let h of z be a complex valued harmonic function on a bounded domain D, such that h of z extends continuously to the boundary of D. All right, if the modulus of h of z is bounded above by m, for all z on the boundary of D, then the modulus of h of z is less than or equal to m for all z in D. So if you can bound the modulus on the boundary of a domain for a complex valued harmonic function, then it follows that the function is modulus is bounded inside the domain. So what I said this theorem means that to bound a harmonic function on some domain, it suffices to bound it on the edge of the domain. All right. So the proof is outlined on page 88, but I point out here that this is really a proof. This in particular, this theorem I just read, is a consequence of one of the big theorems of analysis, which is that the continuous image of a compact domain attains extreme values. This is the extreme value theorem. You've seen it in Calculus 1 when we do the closed set test, right? Like the continuous function attains a min and a max for a closed interval. Well, that's because a closed interval is a compact set. So what this means, what does it mean for it to be compact? It means that there is some ball that fits, that your domain fits inside of, all right? Or your disk here. When I say ball, I really mean disk, a finite radius. And we also need that the real valued function of that domain is continuous, all right? And if that's the case, if it's a continuous function and it fits inside some, and you have a domain and it fits inside some, excuse me, so you have a compact domain that's, sorry, I lost my place here. Well, the point is the extreme value theorem gives us P and Q in the domain for which f of P is less than or equal to f of Z is less than or equal to f of Q. Of course, we're talking about a real valued function here, right? So well, that's, of course, this theorem was about a complex valued function. So I'm not sure what this paragraph is alluding to. In any event, I mostly want you to be aware of the theorem. The result of the theorem, the proof of it isn't especially important to us at the moment. So in the interest of not dragging out this too much longer, most of the reason I wanted to discuss this section at all is for the homework problem that I assigned you guys. All right. So, oh, by the way, So if you have the domain, and then if you union with the boundary of the domain, that gives you a closed set. A domain union with its boundary is closed. And if you have a set which is closed and bounded, then that gives you that the set is compact, all right? And that allows us to apply the extreme value theorem to real valued functions on here, which I suppose would be the modulus. I think that's the heart of the proof there, but let me find, I wanted to share with you guys actually my solution to the problem, because we're a little bit behind and I don't want you to, this is problem 36, so I wanted to give you a rather large hint here. So you're supposed to use the maximum principle to prove the fundamental theorem of algebra. So what I do is I suppose that we've got a polynomial, at least linear, right, of that form. And I suppose towards contradiction that p of z is not equal to 0 for all z, right? If that was the case, then that would mean this did not have a 0, right? Now if that's the case, then what I can do for z not equal to 0, I can factor out z to the n like this, and then I've got this mess right here, all right? And it is not an easy matter, but you can prove that you can choose modulus of z greater than r sufficiently large such that all of these coefficients are less than the modulus of a sub n over 2n, all right? And it follows then that you can bound this thing right here, w, by this sum of things, all right? So you've got this plus this plus this plus this, and when you look at that, that's less than n times modulus of an over 2n. The n's cancel, you get modulus of an over 2. So then what we have is that the modulus of an plus w is greater than or equal to that, which is greater than an over 2. And so what we have then is that the modulus of the polynomial we're looking at is equal to this, but that's greater than this, which is greater than that. All right. And so if we let f of z equal 1 over p to the z, we can notice then that f of z is holomorphic on c because we assume p of z is not equal to 0, right? So we've got 1 over a polynomial, which is never 0. So by usual complex calculus, that's everywhere holomorphic. So we can apply the maximum principle to this thing because it's everywhere harmonic, right? And so if we apply that to the circle of radius r as described above, notice that the modulus of f of z is equal to 1 over the modulus of p of z, which is less than, by our estimate, 2 over a sub n times r to the n, which is equal to L sub r. So the modulus of f of z is less than or equal to L sub r for all z and c, with z less than or equal to r. But as r goes to infinity, L sub r goes to 0, which means the modulus of f of z is less than or equal to 0, which implies then that f of z equal to 1 over p of z equal to 0, which is impossible, which of course contradicts, is a contradiction. And so apparently our assumption that p of z is not equal to 0 for all c is false. And so we find at least 1, 0 for p of z. So I wanted to share this with you. You can, think through it for yourself as well, but that's a sketch of how to solve that problem. I understand this problem can eat a lot of time unless somebody kind of guides you through it, so I wanted to give you a leg up here, especially this part from Churchill. Churchill's a standard complex analysis text that many of us learned from. I learned from it. It's a good book, but it's also, the insight that I have gotten from looking, for example, at this book, Complex Analysis by Saff and Snyder, or your book, Gamelin, is, I don't know, maybe the first book you read is always not clear. But anyway, so the next video I'll make will be on solving Laplace's equation using complex variables. So thanks, guys.